Okay, we start recording here. And let's take a look at the syllabus. Here. That's the syllabus. We are writing here the 21st of October. Laws of motion planning to finish chapter 4 today and start chapter 5. Uniform circular motion. Lab 3, okay, we did lab 3, and lab 3 is lab report. Lab 3 is due next when? Let's see. When is it due? Okay, this coming Wednesday. Report lab 3, okay? Lab report 3 due. And what else? Okay, the exam, second exam is gonna be next week, Wednesday, next week. So far, yeah, we're about to finish chapter 4. Okay, so we're in good shape here in terms of scheduling, and we leave chapter 5 for the exam number 3. Let's do it this way. And I posted the notes for last week's notes, right? Take a look here at the canvas. Okay, we have links for the last video right in here, 16, and let's take a look at the notes. Notes fall 2024. Takes a little bit long to load, right? And here you go. You hear the notes for the lab number 3 and the material that we covered on force of gravity. So let's go here in our notes. I need to open something else too. So hanging down there. And we're going to talk about apparent weight. And we're going to solve some problems of apparent weight as well. Insert the very important type of problem that was apparent weight. 2024, Monday. Okay. Apparent weight. Okay, there's a class of problems. There is a class of problems called apparent weight, which can be solved using Newton's laws of motion. First and second. First and second. Okay. This class of problems explains how astronauts experiment. And I'm going to put it zero gravity while orbiting the Earth. And how fighter pilots experiment higher G levels while flying combat maneuvers. Okay, you don't have to be an astronaut to experiment zero G, and you do not have to be a fighter pilot. One important detail, right? And you do not have to be a fighter pilot to experiment higher levels of G, higher G levels. Okay, you can be a common civilian, and you can go to your local flight school. We have a bunch there in the Southern California area. Torrance, there is that airport in Irvine, John Wayne Airport. They have a flight school there, and you knock at their doors and say, "I want a demonstration flight," and then you ask the instructor to simulate zero gravity with their airplane. Not every airplane that you can do zero gravity maneuvers. You have to be using an aerobatic airplane, and it's a really nice experience. Okay. Maybe you're going to pay like $200 an hour of flight time, and they will show you what feels like experimenting 15 seconds of zero gravity, weightlessness, what that we call, right? And they will show you what it feels like experimenting 5Gs, 5 times the acceleration of gravity. You'll be waiting, right? You have an apparent weight of 5 times your own weight. They can do that with regular airplanes, not just with regular airplanes, but you can also go to your Six Flags, right? And ride the roller coaster, during which you're going also to experiment high and low G levels of acceleration. Your apparent weight is going to be either higher or lower. So, like I said, you don't have to be an astronaut to experiment zero gravity. You don't have to fly a rocket. You don't have to fly the Dragon spacecraft of Elon Musk, right? You don't have to fly that other billionaire spacecraft, Origins, the Origins spacecraft. You can do that with some, either in the roller coaster or by renting time in an aircraft in your local flight school, okay? To experiment. So let's write that down here. To experiment with apparent weight from zero G to higher G levels, you can either go to Six Flags, right? Six Flags. Are they still in business? I was there several years ago with my students from Santa Monica College. Let's see, Six Flags. Most likely they are still in business. Here you go. Headquarters in Arlington, right? Six Flags Magic Mountain in California. Must be this one here. So, which city is that Six Flags Magic Mountain? Los Angeles. Los Angeles, sorry. Hurricane Harbor, Los Angeles, Six Flags Discovery. No, they have, that's in San Francisco. I didn't know they have in San Francisco. Not Soak, not Berry's Farm. Yeah, a little bit east, right? Not Berry's Farm. Never was there. I've never been there. But yeah, we went to Six Flags Magic Mountain. That's the one we went to. My students, just to do some physics experiments in the roller coaster. And there was one ride that was really tough, you know. I didn't expect there was a ride that I believe it was the Superman ride. It felt like they pushed us to 6 Gs, 6 times the acceleration of gravity. Unfortunately, I didn't have recorded that in my cell phone, because our cell phone nowadays, they have accelerometers that can record all the acceleration levels that you're subjected to. Okay, but let's go back to physics, right? To this one I want to close this one here. Yeah. Okay, to experiment with apparent weight from 0 G to higher G levels, you don't need to be, right? Let's see here. You don't need to be an astronaut, neither a fighter pilot, You can either go in a ride. I'm not gonna go in a ride in a roller coaster ride at your local theme park, at your favorite theme park, or go to your local flight school, go to a flight school, let's put it this way, flight school that has aerobatic rides with an aerobatic airplane. That should cost maybe around $200 an hour. You know, when I used to fly those airplanes, they used to charge us like $100 an hour. Right now, because of inflation, but had gone up in price, $200 an hour. Okay, at those places, you can experiment with balls, low G and high G level of acceleration. And Newton's law explains all that stuff, okay? And I'm going to another way to envision these rides is by considering an elevator ride. Okay, think about that. A simple elevator ride. Everybody's familiar with that. And let me get one of my illustrations here. Here you go. Here's an elevator ride. Okay, this guy is inside an elevator. He put a scale in there in the elevator. And the elevator is accelerating downwards at 10 meters per second square. If you manage to get your elevator accelerated at 10 meters per second square downwards, you're going to feel weightless there, like an astronaut, just for a few seconds until the elevator hits the lower floor, right? And here we have another illustration, but in this case it's negative G. Okay? So we have two guys here, both in the using a scale, right? And in this case, the elevator is being accelerated. I put some rocket engines here in the elevator, so it can accelerate at a rate faster than the acceleration of gravity. So let's say this guy is being accelerated at 20 meters per second squared downward. What's going to happen? Whoever is in the proper direction, right, in our direction, is going to feel a negative G. His hair is going up like that. It is as though he would be upside down. And here the scale is indicating minus 80 kilograms. That would be the mass of this guy. Okay? While this other guy here, you know, it's upside down and it's measuring at a weight, right, of 80 kilograms with the scale upside down. For him, it's just the upside down world is just our regular world. Okay, whereas this guy here is the upside down world. For him is the upside down world, right? Because his hair is going upwards. And look at the foot restraint here he has, right? So he doesn't hit his head here at the top of the elevator. But we are going to solve this type of problem using our basic physics concepts, okay? So here you go. Here again is our elevator, okay? But now the elevator is at rest. Our test subject has mass m, and here at the top of the scale, okay? What do you do to solve this problem? Okay, we have to recognize all the forces being applied to the test subject, our test subject here. Okay? And there's a very important piece of information that you must know. What the scale measure, remember, the scale is not a device that measures mass. Very important, okay? A scale that we use does not measure mass. Very important piece of information. What the scale does, our scale measures the force that the scale is applying on us. This exactly this normal force. That's what the scale measures. It happens that we adjust, the force into the mass. We correlate the force with the mass. Okay, let's write that down here. The first important piece of information that we must understand. Okay, another way to envision this ride is by considering an elevator ride. Okay, in this case, you enter an elevator and bring your scale along with you. Okay? Put the scale on the floor of the elevator. On the floor of the elevator. And stand on its top. On the top of the scale, right? If the elevator is at rest, and that's going to be our first example, okay, the acceleration experimented by anyone inside the elevator is zero, right? It's zero. Okay, so that's where we get to do the example number one. Oops. Here you go. I'm going to do all sorts of example here on apparent weight. So you can get this idea. So you can get several different examples of this idea. Okay, consider a test subject of mass m inside an elevator that's at rest. The test subject is at the top of a scale. Find the normal force that the scale exerts on the test subject, which, by the way, coincide with the reading of the scale. Oh, there's more. Divided by G. Okay, that's what we have to write down. Divided by G. Okay. One important piece of information is that a scale does not measure mass. Instead, it measures the normal force that the scale exerts over you. Okay? It just happens that the scale is calibrated to show your mass, which is equal to the normal, right? To the normal n divided by g. Okay? Like that. So let's go back to our scale right in here. We're doing a free body diagram. The free body diagram is going to look at the forces that are being applied only on our test subject. Okay? Like that. Okay, let's see. I'm gonna do like that. Scale at rest. Scale at rest. Find the indication. Find the normal force. Huh? Find the normal force. That's our first problem. Find the normal force. Someone is trying to get in. Let's see here. Camera. 16. Here you go. The situation is like that. Okay, let's I'm gonna here you go. I don't need that. So this guy is on the top of the scale. Let me remove this one as well. Yeah. So let's just play the movie, right? Like I like to do. The first force that we have to take into account is the weight. This individual has a mass m. The weight nearby the surface of the Earth is going to be m times g, which is 10 meters per second square. And it is at this moment that I show the acceleration of gravity. Okay. And then we have to take into account the normal force as well. Okay. Now, wait a minute. Yeah, this one. The other one. Okay, I don't need this one anymore. And then we're going to do the other one. Another example is going to be scale at moving with constant velocity. Moving with constant velocity. Find the normal force. That's going to be the next. Okay, but let's concentrate on this one. Okay, the acceleration of our test subject is going to be 0 because the elevator is at rest, right? So we can go ahead and write down our equations of motion. right? Net force is equal to the weight plus the normal, equal to 0, because the acceleration is 0, right? The weight can be expressed in terms of mg, and that's what I did here. And here's the normal. We want to find the normal, right? And then we can here write our vector. We can here write our normal in terms of minus mg, right? I'm passing this vector to the other side of the equation. That's why we end up with minus mg. But let's not forget that the g can be written, the g vector can be written as g, which is a positive number, times y hat with a negative sign. Okay? And here what our normal, what the value of the normal is, right? The value of our normal is this vector mg upwards. The magnitude of normal is going to be exactly mg, and yeah. Let's see. Okay, I got it. Magnitude of our normal is going to be mg. And that's how you're supposed to use edge scale if you want to find out your mass, right? And because the mass doesn't display a force, the mass doesn't, the scale doesn't display a force, it display a mass, a value of mass. And so what is happening here? Well, what's happening here is that we calibrate the scale to display a value for the mass. And the way we do that, we measure the normal force and divide it by the acceleration of gravity, the local acceleration of gravity, right? And that's how scales are calibrated. They are calibrated to measure mass, to display the value of a mass. But actually, they are, in reality, the scales measure a force, not the mass, okay? Scales are built to measure force. Keep that in mind. But it's possible to calibrate the scale to display the corresponding value of the mass. That's the first example. In the second example, we're going to do almost the same thing. In the second example, we're going to put the elevator to move with constant velocity. That's moving upwards with constant velocity. I'm going to put it here. Here you go. This test subject at the top, find the normal force that the scale exerts on the test subject, which, by the way, coincides with the reading of the scale, right? Okay, there is nothing much difference between this problem, right, and the previous one, because the acceleration is 0 as well. Although the velocity is constant, the acceleration is still 0. Okay, so it's just repeating exactly what we did here in the previous problem. The situation is different, but the final outcome is the same. The final outcome for the force, for the normal force, is the same. And again, that's the right way of using your scale. If you want to measure your mass, you gotta hop into an elevator that's either at rest or moving with constant velocity. Okay. Okay, things becomes a little bit tricky whenever the elevator is accelerated either upwards or downwards. Okay. Consider a test subject of mass m inside an elevator that's moving with a constant upward acceleration. The test subject is at the top of the scale. Find the normal force that the scale exerts on the test subject, which, by the way, coincides with the reading of the scale, okay? And that's something we have all felt. Okay, once you are inside an elevator, the elevator is initially at rest. When the elevator starts to move upwards, I have made G negative, yes. Okay, well, once the elevator begins moving upwards, you feel that pressure on your feet, right? Have you ever felt that? Right. So, well, let me see. Let me address a question here. Can you explain how the y hat made G negative? Okay, let's do that. Right in here, you gotta. We're looking at this one, right? Here you go. See here. Here is the negative sign, Molly. It arises because we define my y-axis being upwards. Okay. That's where you got. Let me do another illustration here. Y hat is this one here, right? Okay, so I'm gonna put an illustration right in here. It's all about how we define the direction of the y-axis. Okay. So here you go. In this specific case, the y hat is upwards, right? But the g vector is downwards, right? Because y hat is upward and the g vector is downward, it must have a minus sign there in front of you once we multiply it by y hat. Okay? That's how we do that. Ruth Mandujano, Ruth is joining us as well. Okay, and now we are going to do this other problem. Okay, at rest. G, okay, so this one. This one here. Scale moving with upward acceleration, It's moving upwards with constant, it's moving upwards with constant acceleration. Find the normal force. Okay, so again, here's my test subject, upward constant acceleration, right? Here are the forces. I'm going to show the force one by one, just like I did before. First the weight, then the normal, okay? And now we have a different situation. Now we have this situation in which the right side of my equation is not going to be zero anymore, right? So going back to our notes, you go. Net force, right? Weight plus normal, there are only two forces there. And on the right side is have the mass times acceleration. And we are going to here write this equation in terms of mg, right? Mg plus n is equal to, and we want to find this normal here. We go ahead and pass and here you go. Let's go one by one here, right? Ma minus mg, right? And then in the next step, we just write the vectors in terms of the unit vectors, right? Acceleration is upwards. Consequently, the sign here of this term must be positive. M magnitude A positive, right? And I'm going to emphasize that the sign is positive. This negative sign here arose because we passed the mg to the other side. Has nothing to do with the sign of g, okay? Has nothing to do. What has to do with the sign of g is this part right here. Because the acceleration of gravity is downwards, we write that down as b minus g y hat. And now we are going to go for the next step. Here you go. Negative minus negative, right? Negative times negative, we get a positive. I'm going to emphasize here the bold face. And now do you see that the normal is going to be more than mg? And you picture that? Here you go. If you haven't pictured it, you're going to be able to picture that right now. I'm going to put m and y hat in evidence. M and y hat in evidence. So what was mg before, now is going to be mg plus m times something else, which is the acceleration. Okay, and now I can write down my final equation. Okay, which is gonna be that. And if I write that down in a scalar format, we write it like that. Okay? That's what your scale is gonna measure. It's gonna measure this normal force. Okay? And if you want to know your mass, your actual mass, all you have to do is to get the normal force measured by the scale and divide it by A plus G. Okay? At this point, you feel an apparent weight that's greater than your regular weight, that's greater than mg. Let's do some numeric value. Okay? Let's do some numeric value. Suppose that the elevator is accelerated upwards at 5 meters per second square. Okay. Okay. 5 meters per second square is half g, right? 1 g is 10 meters per second square. Consequently, 5 meters per second square is half g. So when we write that down here into our equations, okay, we're going to have half g plus 1g, right? And what we end up getting? We end up getting 1.5g, 1.5 mg. Here you go. You're going to your scale, and you really feel that, okay? You really feel heavier. Okay? This is you really feel heavier. It's so, it feels so heavy that it becomes difficult to raise your arms in that type of environment. I was fortunate enough to fly one of those airplanes that NASA uses on one of their airplanes to train astronauts, okay? And I was fortunate enough to fly one of those airplanes, and I had this experience of having a weight, twice the weight, twice my weight. So that's example 3. Now we're going to do another example. Okay. Here you go, example 4. And now this example is a downward acceleration. Right in, okay, right in here, downward acceleration. Still moving downwards. Downwards with constant acceleration. Find the normal force. Just like before, we're gonna play the movie, right? Here you go. The acceleration now is downwards. Here you go. And there are only two forces again. You start with the mg, the first force that we will identify. And after identifying mg, you will identify the second force, which is the normal. Playing the movie, right? Here you go. Test subject with the scale inside the elevator. This one here. mg, mg and normal. Okay, we don't need that anymore. Find the normal force. Find the normal force. So the situation is the same as before. We're going to, to repeat almost everything that we did in the previous example, okay? So here you go. Net force, weight plus normal equal to MA. Okay, the only difference now is going to be the sign compared to the previous problem. Mg plus N is A, MA. Okay, here you go. I'm gonna copy here and paste it. Normal is MA minus Mg. Okay. Here you go. Gonna get next step. Is this one right here. So what's the difference now? The difference now is that the acceleration is downwards, right? Consequently, I need to put a negative sign here. I am emphasizing the fact that this acceleration here has a negative sign. That's why I put the magnitude of A. That's the difference between this problem and the other problem. The difference is right in here in the sign. Okay. And so I can go to the next step and write it down, mgy hat. And this negative is going to go outside. Like that. I'm going to put M and Y hat in evidence. I'll do straight from this guy here. Okay, and here you go, M and Y hat in evidence. Put the parentheses. The M disappear from here because it's in evidence. The Y hat disappear from here because it is in evidence. But don't forget, here is going to be a positive sign And this one is a positive sign. The negative sign ends up here. Okay? To make it look nicer, I just commute the G with the A. Negative. Like that. You got the normal. What happened here? What's this guy doing here? Not supposed to be here. Okay, yeah. Okay, I'm gonna put in terms of the magnitude as well. Here you go. Magnitude would be G minus M, open parenthesis, G minus A. Okay, like that. Which, by the way, okay. If if magnitude of A is greater than 0, and oops, and less than 2G, okay, less than 2G. What happens? What if magnitude of A is less than 2G, right? We're going to experiment, right, with that. What's going to be here? N, it's going to be between what? N let's see, we got, don't forget we're talking about this magnitude here, right? N is going to be less than mg, right? Greater than 0. Do you agree with that? Right? You're going to feel lighter. You will feel lighter. And you will feel lighter. Right? We can even, if A is exactly equal to G, if A is exactly equal to G, what happens? Your normal, you're going to be exactly equal to 0, and you feel weightless. And you will feel weightless. Now, what if I'm gonna put it like that? Let's see, let's put it this way, I. Now we're going to look at another situation here. If A greater than 2G, another situation here. What's going to happen to your normal? Your normal is going to be greater than mg, but the direction is going to be a negative direction, which is exactly this illustration here that you saw. Okay? This illustration here that you saw. Okay. Let's see. Yeah, that's right. Let's see, I'm going to put another one. For exactly equal to G, normal is going to be mg. No? Let's see, in this case, and you will be upside down. You can, well, let's say, and you will be able to walk upside down in the elevator, okay? Elevator, like that. If A is exactly equal to G, the normal is going to be mg. And as before, you will be able to walk upside down inside the elevator, right? So those are the types of problems that we have for apparent weight. Later on, you're going to see another example of apparent weight using circular motion in chapter, in the chapter 5, okay? So we are done with this thing. That's what I want to cover. If we go back, we cover everything that you need. I want you to solve the examples that is in the book, okay? 4.11 and 4.12. Go through the examples that they have in those two sections here. And you'll be able to understand better this concept. So we go. I can highlight, I can boldface this chapter. Okay, what I did here was what you saw here is apparent weight, right? Apparent weight. I can say that this apparent weight with A equal to 0 is one example of equilibrium application of the Newton law of motion, okay? And apparent weight for A different of 0 is just another example of non-equilibrium applications of Newton's law of motion. And any questions? Okay, I'm going to take attendance right now. Audrey Aguilar, are you there? Audrey Aguilar, here we go. I can see Audrey Aguilar here in my roster. Okay, she came in contact with me. Okay, sent me a message, so she's here. Okay. Now, what about Matthew? Are you there, Matthew? I don't see Matthew here. Brianna Carrillo. See, hello, Brianna, are you there? I'm gonna put a star. Brianna's name, Jazzy. Are you there, Jazzy? Hello, Jazzy. Are you there? Okay, Jazzy is not answering me. Gabriel Contreras, Brianna.
Here.
Gabriel is here, right?
Here.
Okay, thank you, Gabriel. Liliana. Let's see if Liliana is here. I don't see Liliana here. Okay, I'll put a 0. Juan Escalera. Juan disappeared, right? I don't see Juan. Molly is here.
Here.
Okay, Molly, thank you. Next is Henry Kim. I saw Henry earlier on. Now I don't see him here in my. Oh, here you go. I see it. Hello, Henry. Must be away from his computer, so let's put a star here. Ruth just joined us, right?
Here.
Okay. Noemi Martinez. I don't see Noemi here. Danae.
Here.
Thank you. Ramon Olivares.
Here.
Okay. Taylor Horn.
I'm here.
Thank you. Stephanie Ramos. Thank you, Stephanie. Jeremiah Reyes. Jeremiah. Okay, thank you, Jeremiah. Next is Sean Rosario.
Here.
Thank you. Ali Standard. Hello, Ali.
Hello, I'm here.
Okay, thank you. Jason Street.
Here.
Next, Elena Trujillo.
Here.
Thank you. Thank you. Jason Valadares.
Here.
Next, Stephen Vatapali. Stephen Vatapali. I don't see Stephen here. Okay, Jeremiah. Next is Laurel Williams. Thank you, Laurel. Nohamin Wandimu. Thank you. Next is Aliyah Zavala. I don't see Aliyah here. Now let's see how many students we have. 17. 2 students who didn't answer. 19. Okay. Let's see, one more opportunity here for Jazzy. Are you there, Jazzy? Okay, thank you, Jazzy. Henry, are you there, Henry? Okay, let's leave this way. We're gonna have our break now. It is 9:50 a.m. Break till 10:05 a.m. Okay, so I see you soon, and we're gonna start a new chapter. Don't forget the exam is up to the end of this chapter, right? Chapter 4. I see you in the next few minutes. I'm sharing the screen. Let's see. Okay. Is Henry there? Are you there, Henry? Elena is trying to come in. Okay. Cat. Now we're going to start chapter 5. Okay, let me copy and paste the material for exam 2, right? Okay, which we had that those topics of chapter 1 in exam 1, so it's not going to show up in exam 2. However, don't forget, you know, the material is cumulative, right? Whatever we covered in chapter 1, you should have to know. You should have to know for the exam, just like the case of vectors, right? How to expect to solve problems of chapter, the problem of chapter. Of chapter 3 and 4 if you don't know vectors, right? That's I want to this one here. I want this one. Chapter 3. You go 3, 1, 3, 2, 3, 3, 3, 4. Okay, 3, 1, 3, 2, 3, 3, and 3, 4. Okay. In chapter 4. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a long chapter. 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8, 4.9, 4.10, 4.11, and 4.12. Labs 2 and 3, yeah, lab 2, lab 3. We'll start chapter 5 now. So uniform circular motion, chapter 5, uniform circular motion, and I'm going to use the abbreviation UCM for uniform circular motion. Okay, so uniform circular motion is the circular motion at constant speed, not constant velocity. Remember that, right? There's a difference between velocity, constant speed and constant velocity. The magnitude, constant speed means that the magnitude of the velocity does not change. But just by saying constant speed does not guarantee that you have constant velocity. Just like in the case of uniform circular motion. In the case of uniform circular motion, the velocity vector is changing direction, right? It's not changing magnitude, but it's changing direction. And circular motion is just another example of 2D motion. We saw some types of 2D motion before, and now we are going to see another type of 2D motion. Okay, and at this point, I want to introduce you to another type of coordinate system. Another type. Remember, there is you're already familiar with Cartesian coordinate system, right? But then there is another type of coordinate system that we call the polar coordinate system. Okay, here you go, Cartesian and polar. I put it. The Cartesian coordinate system is represented by the coordinates x and y. And the polar coordinate system, by contrast, is represented by the coordinates r and theta. I want to illustrate this coordinate system, and we have to get another illustration here. Let's see here. Right in here. Okay, so I'm going to transfer those things elsewhere. All those drawings here, I have to save as, browse, navigating inside my hard drive, 06 UCM, uniform circular motion. And why am I introducing this polar coordinate system, right? There's a reason why I'm introducing this polar coordinate system. Here's an example of uniform circular motion, right? The particle undergoes a circular trajectory. And what I'm going to do, I'm going to simplify all the stuff for now. Okay, so here you go. Yeah, and let's say the particle undergoes uniform circular motion in a circle of radius lowercase r. Okay, the vector position of this particle can be either denoted by the coordinate x and y, right? Here you go, here is x. Here you go, here's the position vector of the particle. Position vector of the particle. And this position vector is denoted by the vector r. Yeah. Nope, didn't do it. Let's see if I can get that. Okay, good, I got it. Yeah, r vector. here, I'm going to, and that's one vector that we can put it here. And I'm going to erase this guy too. So making things simpler, right? And to play the movie, right? You start with the X and Y coordinate system. That's it. Let's play the movie, right? Start with the X-axis. Here you go. This guy goes right in here. And then we finally get Y-axis. Here you go. Then we show the path of the particle. Oops. And this guy here is going to be sent to the back. Sent to the back. So, yeah, sent to back. In our next step, we put, oh, by the way, this circle is a circle of radius r, lowercase r, at this position here. X is equal to r and y is equal to 0. At this other position here, y is equal to r, lowercase r, and x is equal to 0. On the opposite side, you have x equal to minus r, right? And y equal to 0. On the other side, in the lower side here, y is equal to r, and x is equal to 0, right? The exclamation point here means that we know r. What's the value of r? And in my next drawing, I'm going to put my point particle there and state that it has a non-mass m. Point particle. In the next slide, in the next frame of my movie, right, we have the vector r. Let's see. Yeah, I'm gonna get better off. Here you go. Here you go. Vector r. In my next frame, we're going to denote the r hat, the vector r, the unit vector r hat. Okay. Let's see. Let's play the movie. What we have so far? X-axis, Y-axis. Oh, what's missing here? The origin, right? Let's put the origin here. The origin 0. And then we gotta copy this 0 here and place in the other one there. Here you go. Origin 0. Circular path. Okay. Now the radius of the circle. Lowercase r. The point mass at a given position in the circle. The vector position of the mass. The unit vector of the vector position. Magnitude 1, right? And now from chapter 2, recall that the velocity vector will always be tangent to the path. Remember that? The unit vector always tangent to the path. Here you go. And we also know from chapter 2 that the acceleration vector is going to point towards the center of the circle, the center of curvature. What you should not know is that this acceleration vector is going to point exactly to the center of the circle because it's a uniform circular motion, due to the fact that we're talking about uniform circular motion. Here you go. Better now. I'm going to prove that, right? It's not difficult to prove that. Now we do not need that anymore. We do not need that anymore. Okay. But I was talking about the polar coordinate system, right? In order to talk about the polar coordinate system, I'm going to take those vectors out. So it's not that too busy, right? Okay, in the polar coordinate system, we have what we call the radial coordinate, R. Okay, and we also have the theta coordinate that I'm going to represent here. Grid lines, yeah. Like that, huh? Here you go. So here you go, theta coordinate right here. I'm doing, I'm representing those coordinates in the polar coordinate system. Theta is like the Q letter in the keyboard. And then you convert that into the symbol. And I'm going to put it in a different color. Let's see which color. Yeah, I'm going to use this one here. And the angle tool will be right here. Okay. And by the same token that I can describe the position of this particle in the polar coordinate system, okay, I can also describe, by the same token that I can describe the position of this particle in the Cartesian coordinate system, I can also describe, I don't need that anymore, right? Let's see, do I have any other thing here that I can get rid of? I don't need that either. Okay. And I'm going to write down here the coordinate system, the Cartesian coordinate system. Here you go, X and Y. Oops. Here you go. We can also describe the position of this particle in the polar coordinate system as well. The polar coordinate system will have a lowercase r and an angle theta. And there is a relationship between those two coordinate systems, okay? The polar coordinate system is very convenient to use whenever we have this type of motion, like a circular motion. Notice that X and Y here will vary along the path of the particle, right? But in the case of the r theta, only theta will vary throughout the path of the particle. Only the coordinate theta will vary, whereas r is going to be constant. That's why it's convenient to use this coordinate system in this type of motion, okay? So going back to our notes. Okay. It is far more convenient to use a polar, the polar, right? Not a polar, the polar coordinate system whenever a particle describes circular motion, describes a circular path. Let's put like describes a circular path, right? It's far more convenient to use the polar coordinate system whenever a particle describes a circular path. And there is, okay, that is because the coordinate r is constant, whereas both x and y are not constant. Okay, and that's shown right in here in this table. There is a relationship, you know, that there is a relationship between the Cartesian coordinate and the polar coordinates. And it's not that difficult to visualize, okay? Coordinates, okay? All you have to do is to go back to the drawing and note that the x position here along the x-axis is given nothing but r cosine of theta, okay? Simple enough, right? So here you go. By simple visualization. Like that, x is what? R cosine, like that. And y is r sine, right? When we want to go from r theta to x and y, we apply these two equations, okay? From x to y, from r theta, from polar to Cartesian. Okay. Now, if you want to go from Cartesian to polar, what do you have? We have something like that. X. Let's see. I'm gonna put it like that. R squared is equal to x squared plus y squared, right? Which is the equation of a circle. And then if we want to go from, if you want to find out the angle theta, what we have to do? All we have to do is to divide this equation here by this equation here. And then we get what? Tangent of theta equal to y over x, right? From Cartesian to polar. Okay, we can have another, you can come up with another step here. Go. we put a square root right in here for this term. And we represent just by r. And then we take the inverse of this function. Arctangent. Arctangent of y over x. That's how we change from one coordinate system to another one. Okay. So if you have your coordinates x and y and you want to know r and theta, you use this transformation right here. Okay, if you have r and theta and you want to know x and y, you use this transformation right in here. Okay, so let's go here. You have already been introduced. You have already been introduced to 3 coordinate systems, right? Coordinate system. One, the first one, 2D Cartesian. 2D Cartesian. X, Y, and Z. The other one, 3D Cartesian. Oh, sorry. 2D Cartesian doesn't have a Z here. X, Y, and Z, okay? 3, 2D polar, R and theta. And there is a force coordinate system that I want you to remember too, right? There is one more that's rather straightforward. There is one more coordinate system that is rather straightforward once you know the polar coordinate system. Okay, and this for one, this force one is the cylindrical coordinate system. Which, is going to be given by r, theta, and I'm gonna put it here, 3D cylindrical r, theta, and z. Okay. That should be the fourth one here. Can you picture them all? Let me draw them for you. Vector, maybe this one here. The motion examples. Let's see if it is here. Oh yeah, here you go. That's the one I want. Going back to the previous one, 6 UCM, right in here, 3D, right? 3D coordinate system. I can even come up with my vector position here of this particle in the 3-dimensional space, going from the origin to the point x, y, z. X, y, and z, right? But we also have the cylindrical coordinate system that's going to denote my coordinate. Oh, it's the same, right? Yeah. Yeah, better. In addition of, instead of X, Y, Z, is going to be R. Let's see how I'm going to draw this thing here. That we are going to have this one right. Let's see. Yeah. Let's see. Not this one. I'll have to do a little bit of a magic here. Let's see. No. Like that. Can you believe that? A little bit odd, right? That would be the theta. The theta coordinate. Yeah, better now. That will be R. Is in the X. The theta angle is in the XY plane. Symbol. And then we have the Z coordinate, which is this one right here. Okay. Not only we have the R, X, Y, Z, we also have the R, theta, and Z, right? And the transformation from one to the other is exactly the same that you saw before, because this Z here is exactly the same Z. The Z in the Cartesian coordinate system is exactly the Z in the cylindrical coordinate system, okay? There is another coordinate system, just for you to know, there's another coordinate system. We're not going to play with it right now. There is one more important coordinate system called the spherical coordinate system. Okay. 3D spherical. This coordinate system is represented by the radial direction, radial distance from the origin of your coordinate system, an azimuthal angle phi, and then we have another angle theta, okay? This angle theta is related to the latitude of the point. It's related, it's not exactly the same, but it starts from the pole of the sphere. That's how you count, okay? So let's go back now to uniform circular motion, okay? What time is that? 10:40, okay. Like I said before, in uniform circular motion, it's far more convenient to use the polar coordinate system, because why? The magnitude of the position vector is constant and given by the radius of the circle r. Okay, I was using lowercase r, right? Let's use lowercase here, although its direction varies. Going back here to my drawing of my point, right? I can even start animating this thing. Let's see if I can do that. Let's do that. Let's animate this guy here. You know, that's the initial position, right? So a little bit later on, let's see here. I can size and position. So rotation, I'm going to rotate, no, the other direction. Let's rotate 10 degrees. Reposition this vector right here. Increase the angle, right? Theta. And the particle is placed right here. I'm going to make things easier here. This one. And take this one out, take this one out, take this one out, right? That's the first frame of my movie. The R vector has moved as well, must move as well, right? In the next one, notice that I'm just changing the angle of this vector. I'm gonna go 10 by 10 degrees. See here. Format, size, and position. Every 10 degrees. 10 degrees, 20 degrees now. I'm not changing the length of this vector, right? I'm only changing the angle that this vector makes with the horizontal axis. One more. Size and position, here we go. Now I have 4 frames. And then we can play our movie. 1, 2, 3, 4. Here you go. Right in here first, a little bit later is here, a little bit later is here. Notice that the length of the vector is not changing, right? Only the angle is changing. On the angle that the vector makes with the horizontal. That's why it's convenient to use the polar coordinate system. Okay. The tangential velocity is constant and parallel to the unit tangential velocity on the theta direction. Okay, the tangential velocity is constant and parallel to the unit vector along the theta direction. Okay, and let me show you. I didn't show you every vector that I was supposed to show, right? So I already showed you the unit vector along the radial direction. Let's go back here. I'm going, yeah, here you go. I will use this one right here. Erase. Oops. Yeah. Okay, I showed you this unit vector for the R hat. But on the top of this unit vector, we have another unit vector. The unit vector related to the angle theta. Okay, here you go. If this angle here is the angle theta, then we can also come up with the unit vector theta hat. I'm going to make it that color blue. Yep. I'll copy this one and paste it next to it. Okay, theta hat. And I'm going to put it as this nice blue color. So we have the coordinate theta, and then we have the unit vector theta. And this unit vector theta is parallel to the velocity vector, right? So here you go. The unit vector is here. If the unit vector is here, unit theta vector is here, then the velocity vector, let's get them. Let's get it. Okay, is this one right in here? It's gonna be this one here. Tangential. The two must be, I'm gonna slide this one a little bit off. Yeah, like that. But it should be, they should be parallel to each other. Yeah, theta hat. So we use this guy here, P. And make it a red color. Okay, P is parallel. No, let's see if I can find it. Nah, he's not gonna cooperate with me. Okay, let's leave this way. Those two vectors are parallel to each other. Tangential velocity is constant and parallel to the unit vector along the theta direction. Okay. The radial component of the velocity is 0. The tangential acceleration is 0. And the radial component of the acceleration is constant along this direction, although its direction varies. Okay, we can prove all of that. And now we can display the acceleration vector right here. I got rid of it before, right? Let's see. I need to. This one here. Let's see. Nope, overshoot. Yeah, this one right here that I want. Okay. Now I'm going to erase this one here. All right. So you can see the centripetal acceleration. Okay, how do I know you have only, how do we know that the acceleration is towards the center, right? How do I know the acceleration is exactly towards the center? We know the acceleration is exactly towards the center because this vector velocity here doesn't change in magnitude, okay? The acceleration must be perpendicular to the vector velocity. If the velocity doesn't change, the acceleration must be perpendicular to the vector velocity. However, if the vector velocity were to change in magnitude, the acceleration vector would have a component that would be parallel to the velocity vector. Make sense? Okay? Let me go back here. I'm going to write that down for you in the notes. Okay, so here you go. The magnitude of the position vector is constant and given by the radius of the circle r, although its direction varies. The tangential velocity is constant and parallel to the unit vector along the theta direction, right? Recall both coordinates r and theta have a unit vector associated with them, okay? The radial component of the velocity is 0. Yeah, that comes from the chapter 3, right? Chapter 3 on 2D motion. The tangential acceleration is 0. How do I know that? This is consequence of the fact that the velocity is constant. Not the velocity, sorry. The speed is constant. Okay? If the speed would change, it's constant. Okay, we were supposed to have an acceleration component that is parallel to the velocity vector. Since the speed doesn't change, since the speed does not change, okay, the acceleration vector must be perpendicular to the velocity vector. And the radial component of acceleration is constant, although its direction varies. Okay. This is consequence of the very definition. This is consequence of the very definition of this type of motion. This type of motion, uniform circular motion. Circular motion, okay? So now I can tell you about each. We have this table here, uniform circular motion, Cartesian versus polar coordinates, right? For the position, you already know that x is a function of t and y is a function of t. R is constant. I'm gonna keep it consistent what I have been doing so far. But the theta angle is a function of time, okay? For the velocity, this thing here we already saw, right? We already saw this first one. What we didn't see is the other three lines here. Okay, for the velocity vector, the x component of the velocity is going to be a function of time as well. Not just the x velocity, x component, but also the y component of the velocity. Let me make it look nicer. Okay, here you go. But in uniform circular motion, there is no radial component of the velocity, right? See that V sub r is equal to 0. The particle is not moving away from the circle. It moves around the center of the circle. It's not moving away from the center of the circle, right? It's moving around the center of the circle, right? Okay, so velocity, right? And no radial component. In other words, the particle is not moving away from the center of the circle. Instead, it is moving around it. In other words, around it. But because the velocity is uniform, the theta component of the velocity is going to be constant. Okay? See how everything is much simpler in polar coordinate for this type for this type of motion. Here, you know, half of the coordinates are constant in the polar coordinate system. But here, the components, they are both constant. One is 0, the other is constant. The acceleration, you're going to find out the x component of the acceleration is going to vary as well. Okay. The direction in both cases is gonna change in time. Oh no, here, oh, sorry. The direction here, the x hat and y hat are going to be constant, right? But not in the polar coordinate system. The polar coordinate system, the r hat and the theta hat is gonna change. R hat and theta hat. So that's the only difficulty that we find here in the polar coordinate system. That's the only, you know, disadvantage of the polar coordinate system compared to the Cartesian coordinate system. Everything else here is an advantage. So here you go. In the case of the acceleration, the x component of the acceleration is going to change as time goes by, whereas the radial component of the acceleration, I can prove to you, is going to be a constant. And because we are talking about uniform circular motion, the tangential component of the acceleration, the theta component of the acceleration, is going to be 0. Okay? 10:58 right now. Let's take a little break now. Okay. We have 2 more minutes. Let me write that down here. Velocity acceleration. Acceleration components. Radial is constant. No, tangential is 0. Okay. Tangential, or theta hat, right? Or theta hat is 0. Okay, so let's have our break right now and break. Any questions? Let me see. Am I missing any questions from you? Let's see. Okay, I'll break from 11 a.m. to 11:15 a.m. Okay, well, I'm going to see you shortly. I'm back here, and let's now get the equations of motion of this particle. Okay, that's the idea here. We will now find the equations of motion of a particle that undergoes UCM, uniform circular motion. Okay. For the position, you know, the equation of motion is rather straightforward. The equation of motion is rather straightforward to find. Straightforward to find. You know, just by looking at the illustration, right? We found the following, and I even have already displayed that for you, right? Here you go. X, right? X divided by the radius of the circle is cosine of theta, right? That we saw that before. I'm gonna here you go. I'm gonna simplify this notation for now. We saw that before, right? Here you go. I'm gonna put a different format here. Different format. Here you go. R goes right in here. From this equation, we will be able to find the equation of motion. And how do we do that? Okay, just by realizing that this theta angle is changing as time goes by. This theta angle is a function of time, okay? And then we are going to find out what's going to be, oh, don't want that, I want like that. Okay? The challenge now is to find this relationship here for theta. Okay. So given B, right? And R, find the theta as a function of time. Okay, that's the challenge that we have in order to complete our problem here. At least the first set of the equations of motion. Okay, there is a definition for angle, by the way. There's a definition for any angle. The definition for angle is given by what? You know, there's something that we should have learned some time ago. It's going to be the length of the arc divided by the radius of the circle. That's the definition of an angle. Okay? If you apply that to the specific case of a full circle, right? Note that for a full circle, here you go, let's write it down here. Note that for a full circle, right? S is going to be equal to what? 2 pi r, right? That's what S is for a full circle. And when we substitute this relationship here in the angle for theta, what do we get? That's just a special case, okay? We're working just a special case. We get exactly what we expect to get. We get a theta equal to 2 pi, right? Which makes sense, right? Which, by the way, is 180 degrees. Yeah, 180 degrees, right? So this relationship does make sense. Even if you're not familiar with that, you can apply this special case and you're going to get a consistent result, okay? So here you go. What else? What else can we do with this definition? Going back to our definition, right? Going back to our definition of angle. Going back to our definition of angle, note that S can also be written in terms of Vt, right? V is the velocity of the particle or the speed of the particle, right? And T is the instant of time, or here you go, or S, the arc described by the particle at a given instant of time can be given by V times T. And now we can use this relationship right in here in this equation for theta, and we finally get our equations of motion for the X and Y coordinates, Vt. Okay? So here you go. Not only for the X and Y coordinates, but also for the R and theta coordinates, right? Cartesian coordinates. Cartesian coordinates. That's gonna be VT over R. And that's gonna be VT over R. I'm going to erase that. I'm going to erase that. Polar coordinates. Polar coordinates. R is a constant. And theta, we found it before, is VT over R. Okay. Okay, for the velocity, it's a little bit more difficult. For the velocity, the derivation is a little bit more difficult. Okay, going back to the drawing board, right? Here you go. Here's my drawing board here. I'm going to isolate my velocity vector so you don't get distracted by anything else, right? Here you go. The only thing I'm going to put back there, let's see here. I don't want this one. I want the other one. Don't want that. Okay. Oh, I shouldn't have done this one here. Right here. Okay. Let's get my angle theta here. I'm going to need that. Yeah. Okay. And I'm going to do something else. I'm going to draw a horizontal line here. So you can situate ourselves. There's a reason. Okay. This angle here is theta. Consequently, this angle here must be theta as well, right? So here you go. We have to do this analysis. Okay, here you go. This angle here is theta as well. This angle here is 90 degrees, right? Consequently, this angle here must be 90 minus theta. Okay? I'm gonna copy and paste. Here you go. I'm gonna put a different color. Green. Nope, it's not what I want. This one here. Yeah, this one here. 90 minus theta. -90 minus theta, and superscript, and I'll put it in the green color. Go. Oh. Yeah. Green. Good. Okay. And now we can break down the components of my velocity vector. The velocity vector will have a x component right in here and a y component. Okay? My x component is going to be minus v sine of theta. Can you see that? If this one is 90 minus theta, this angle here is going to be theta. Okay? Or even better, that's, let me shrink it a little bit more. Right here. Cosine, another way to look at that, the x component is v cosine of 90 minus theta, minus v, right? From the drawing, here you go. But the last derivation is a little bit more difficult. Here you go. But can be obtained by breaking down the velocity, the components of the velocity vector. Okay, so here you go. V sub x is, here you go, v minus v sine of theta, right? And theta is what? Vt over r. I'm gonna put like that. Like that. Vt over r. Going back there. Not this one. This one here. Right? It's cosine of 90 minus theta. Cosine of 90 minus theta is sine of theta. And then we have for Vy is plus V cosine of theta. Cosine of theta, like that. Okay, so you got 4 out of the 6 equations. Okay? 4 out of the 6 equations. And for the acceleration vector, we have the following. Okay, let's go back here to the acceleration vector. It's not obvious, but I'm going to show you such a note. See that my acceleration vector is contrary to my position vector. Okay? Do you see that? The centripetal acceleration doesn't have a tangential component, has only a radial component, but it's a radial component that's opposite to the unit vector of position. So, because of that, we can use this equation here to find out the x and y components of the acceleration. Okay? They are going to have a negative direction. Okay? And the only thing that's going to change, this doesn't change, this doesn't change. The only thing that changes is the negative sign and also the magnitude of this vector. That's going to be A, which we still do not know, Okay? There is a very A there. I'm even going to say, CP, okay? To stay, let's call it CP, ACP, just to be consistent with what we drew in there. We still do not know what ACP, what is the relation between ACP and the what is the relation between ACP and the non-variables parameters, right? I'll write it down. V and R. This can be obtained by using arguments of geometry. Okay? And your book spelled that out in a very nice way, which we are going to repeat here. Okay? How do we do that? We do it in the following way. I'm going to get this drawing, and I will get the other drawing as well. Here you go. This other drawing here. Okay? Here you go. We have a velocity. I'm going to erase this guy for now. Erase it, erase it, erase it, and erase it. Erase it, erase it. This velocity vector, I'm going to call it V1. Okay? And this other velocity vector here, I'm going to call it V2 because they're two different vectors. V1 and V2. And I'm going to combine them in a single drawing. V2. So you can see them more easily. All right, here you go. I'm going to combine those two drawings into a single one. Let's see. I'm going to get that. And, oh, not good, but that's okay. I think I can. Good. Okay, I got rid of some of it. Let's see if I can get rid of it. Yeah, this one. I don't need that. Yeah, and that should be theta 2, right? But I don't need that. I don't need that. Okay. Very important. It doesn't look like, but let's see. I want to ensure that I have everything drawn properly here. Rotate. I'm going to rotate it. Yeah. Okay. I want to make sure that V1 and V2 have exactly the same magnitude. By the same magnitude, I mean the same lengths, right? Okay, so now they have the same lengths, right? And I'm going to I'm going to write that down here. V2 is equal to magnitude of V2 is equal to magnitude of V1. Why is that? Because we're dealing with uniform circular motion. That's why their magnitude are the same. Okay. Yeah. Like that. Okay. Which I'm gonna call V. Yeah. Scalar V. Okay. To simplify my notation. And now we're going to do something else. I'm gonna get back my R position, R vector position here. Okay. This one is going to be R2. And the other one is going to be what? R1. And I'm gonna rotate it just a little bit. R2. And the other one is R1, right? Make sense? Just like before, this relationship also holds for the vector positions R2 and R1. R2 is equal to R1, right? The magnitude, right? Just the magnitude, which is equal to our length R. And I'm gonna put it in a different color. Like that. But there is more. There is more. This angle here ends up being equal to this angle between those two vectors. Okay, it's possible to prove that. Okay, so here you go. I'm going to transfer, here, V2, V1. V1 and V2, okay? The angle that those two vectors R1 and R2 makes is equal to the angle that those two other vectors make with each other. Okay? It is possible here, theta 1, theta 2, okay? Yeah, here theta 1 and theta 2, okay? From this, we end up having that the triangle V1, V2, the triangle that V1 and V2 makes, let's see, I'm gonna get that, is similar to the triangle um, 2 minus V1. This triangle here is similar to this other triangle here. They're just oriented differently, but the triangles are the same. Okay, I'm going to take a drawing here. Here you go. I'll get this guy exactly here. like that. This angle here. And this other angle here. And they are exactly the same. And I'm going to center it right in here. Like that. What time is that? 11:44. We're getting there. This angle here is the same as this one. Okay. Consequently, because the angles are the same, and this length is equal to this length, those two different drawings make up a triangle that are similar. Okay? So here you go. Let me write that down here in the notes so you can follow. Okay? Note C that V1 and V2 vector. Let's see here. V1 and V2 vectors form a triangle that form a triangle that is similar to the triangle formed by R1 and R2 vectors. Okay? The velocity vectors at 2 points, okay, at 2 distinct points in the circle, on the circle, form a triangle that's similar to the triangle formed by the R1, R2 vectors. The position vectors are to distinct points on the circle. Okay? In other words, the angle between V1 and V2 is the same as, for the following reason. Here you go. For the following reasons. One, the angle between V1 and V2 is the same as the angle between R1 and R2. Okay? For the following two reasons. And two, one reason is not enough. Okay? You have to have a second reason. And two, R1, magnitude of R1 is equal to magnitude of R2, and V1, magnitude of V1 is equal to magnitude of V2, okay? So like I said, just having the same angle is not enough condition for those vectors to form a similar triangle. Their lengths, you know, here you go. Their length must be the same as well. Okay, isosceles forming isosceles triangle, right? Triangles, two isosceles triangle. let's see, I'm going to get this one here, so make it, so it looks better, right? Here you go. 1, and then I'm gonna put the vector in there. Here you go. And V2. All I have to do is to change V1 here. The angle between V1 and V2 you go, is equal to the angle between R1 and R2. R1 and R2. Oops. Okay, R1 and R2. I'll get that. R1 and R2. And then I'm going to I have to state that those two. And this holds because in the first case we're talking about a circle. In the second case, we are talking about uniform circular motion. The length, right? Is equal. We're not done yet, right? I'm going through the whole 9 yards here to prove to you that what you have here is two similar triangles, okay? Now we're going to go to the next case, okay? Similar triangles. I want to put that here. Yo, let's see this one here. Similar triangles. Similar triangles. Similar triangles, okay? Why are we doing that? There's a reason why we are doing that. In case you have forgotten, right? We're doing that because we want to find this guy here, right? That's why we're doing that. That's why we're going through this trouble. This thing is okay, we already know because V and R is known. And the acceleration is given in terms of the variable t, okay? Now, what about this guy here? We can prove that what this guy is, okay? Recall that our ACP is in reality our acceleration, right? Now, recall that ACP is our acceleration A. There is no tangential component of the acceleration. Consequently, the acceleration vector can be written as, also recall, right? Also recall that the acceleration vector is given by, no. Yeah. Let's get that. This one here. The acceleration vector, back, is given by what? The definition, the very definition of acceleration vector is what? Delta V over what? Delta T, right? In our specific case, my delta V is going to be what? V2 minus V1. Okay? V2 minus V1 over delta T. Going back to my drawing, to the drawing board, right? This one, V2 minus V1 is going to be what? Is going to be, let's say, we got to invert the V1, right? Let's invert the V1. And right? V2 minus V1 is going to be this vector right in here. And all those three vectors, and don't forget, it's going to be a vector that's parallel to the acceleration vector, right? A vector that is parallel to the acceleration vector. Let's write that down here. V2 minus VO. V1. Like that. I'm gonna put it in a different color so we can get it, okay, like that. V2 minus V1. And let's not forget that we also have this other vector, right? I'm gonna put the black color as well. R2 minus R1. R2 minus R1. 5 more minutes. We are almost there. Oops. Yeah, R2 minus R1. Okay. And now that we have those similar triangles, let's see, I'm going to orient them in the same direction, group them all. Okay, here you go, like that. Okay, here you go. This is R2, this is R1, this is R2 minus R1. And I will select them all and drag to the middle. Yeah. Okay. They are all similar triangles. Both of them are all those two triangles are similar because this angle is the same and this side is equal to this side as well. This side equal to this side. Okay. So what else? There's more. Okay. So here you go. Going back to my notes right in here. Okay, now this V2 minus V1, okay, is going to be, there must be equal to the acceleration, right? And there is, Going back to the triangle here. Here you go. Okay. Let's take a look at the book. Sorry. You go right in here. I'm doing exactly what the book is doing. Okay. Here you go. The V vectors, right? Delta V. And then what we have here? We have that this length here, delta V over V, the length of this side of the triangle divided by V must be equal to this length that you see right in here, V delta T over R, because they're similar triangles, okay? Okay, so because the triangles are similar, we must have the following. We must have the following relation. Okay, you go delta V, right? Over V must be equal to VT over R, like that. Okay, here you go. Let's call V delta T, right? V delta T, which is the difference of time between one point and another. Okay. I want this V to look better. And let's not forget this thing here is a magnitude. It's not a vector because we are talking about the length of a side of a triangle. Okay, and then there's more. We're almost there. Note, see that I'm gonna pass this delta T here to this side. Okay, and this V is gonna go to the other side, multiplying the other V. V times V is V squared. And delta V over delta T is what? Delta V over delta T is in reality the magnitude of your acceleration. Okay? In this case, it's going to be my centripetal acceleration. Okay? That's how, and then we finally get the magnitude of this acceleration is V squared over R. 1201 already. And now finally, we have all the equations of motion for the position, velocity, and acceleration. I can write that down right in here. V squared over R and V squared over R, okay? So we run out of time here, 1201. Do we have any questions? I have office hours right now. If you wanna know, if you wanna ask any questions, I'll be here for the next hour, okay? And let's see, someone left a message here. Let's see, nope, okay. So I see you on Wednesday, the day after tomorrow.